In the last section, we introduced the concept of a power series, and now in 11.9 we're going to be looking at the representation of functions as power series. So we're kind of flipping the question or our interest in power series upside down on its head. We want to, as opposed to what we did last section. In the last section we started with a power series and then found its sum. Now what we want to do, and actually I want to make this pen darker blue. Now what we want to do is we just want to start with a function, and we would like to be able to find its power series representation. So what's the difference? What are we doing different? And last time when we were given a power series, we answered all kinds of questions about, and just to recall, remember, a power series looks like this. It's a sum from n equals 0 to infinity of c sub n x minus a to the nth power, right? It looks like c0 plus c1 times n x minus a plus c2 times n x minus a squared plus and so on. If a is 0, then it may look like c0 plus c1x plus c2x squared plus c3x cubed, and so on. It's a series in that it's an infinite sum. It is a power series because every term of the series contains a variable x raised to some power. Okay, this is the 0 power, first power, second power, third power term, and so forth. And so we explored with a series like this, what does it converge to? Under what values of x does it converge? Can we find its interval or radius of convergence? And those sorts of things. But now what we want to do is we want to go the other direction. And this is where it's most useful, because we're going to find functions that are difficult to work with in general, but if we can find its power series representation, then there's a whole lot more we can do with that function that we couldn't do otherwise. So we're going to do this in two sections. We're going to do 11.9, which is this section, and I like to call this the clumsy way. What we're going to be looking for is anything close to a known power series and to modify it to look like that known power series. And then 11.10 is a much more elegant solution to come up with a general formula, and I would call that the Taylor series. We're going to look at something called Taylor series and also the Maclaurin series, which is a special case of the Taylor series. So let's start what I call the clumsy way. Let's eyeball it and see if we can find something that works. So first of all, we're going to find the power series for this function right here, f of x equals 1 over 1 minus x. And we're going to do it by pulling something out of thin air. Okay, instead of doing anything with this, let's just go back and look at this series right here. Okay, if you stare at it long enough, hopefully it becomes familiar. You recognize it as a type of series that you've seen before. Hint, 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 right here. It's a geometric series because you have a constant ratio being multiplied by each term to get to the next term. Your ratio in this case is the variable x. Your initial value, which we typically call a, is 1, and you'll remember that a geometric series converges so long as the radius of it, so long as the ratio r has an absolute value less than 1, and then it converges to a over 1 minus whatever r is, a being the first term of the series. So since r and x are the same thing, notice this series here is going to converge if the absolute value of x is less than 1. And what does it converge to? Well, it converges to a, which is 1, over 1 minus r, which is x. Hence this function f of x. Again, so long as the absolute value of x is less than 1. So we're going to call that the power series representation of this function f. So we just got lucky. This is the power series for this function. And so for all the other questions in this in this section, we're going to be trying to take a function and make it look as much like this as possible, and once it looks like this, then we can find its power series. Okay. Now, to explore again what we mean by saying it's a representation of that function, I'm going to jump over to Desmos, and I want to plot a few of the partial sums of this power series as polynomials. Namely, I want to plot the function, say, 1, and then the function 1 plus x, and then the function 1 plus x squared, and then the function 1 plus x squared plus x cubed. I'm just taking consecutively more terms of this series. I want to plot what those polynomials look like and compare them to this function f of x. So I've gone to desmos.com/calculator, one of my favorite tools that we've used to play with and explore some functions here. I've typed in 1 over 1 minus x, and if you put inside curly braces a restriction on the range of values, or I should say domain of the value, the set of x's. In this case, I put that the absolute value of x is less than 1. It's only going to plot where x in absolute value is less than 1. So from x equals -1 to +1. Notice this is an asymptotic function in that it is approaching infinity as we get closer and closer to 1 from the left-hand side. So what I've done is I've gone through and I've included what happens. I'm going to turn this off. What does the first term of the power series for this function look like? Again, remember our power series looks like this. It is over here 1 plus x squared plus x cubed and so forth. So if I now plot that in Desmos, the first one, if I just plot the first term, y equals 1, it's just this straight horizontal line. Boring. So at least they agree at x equals 0. They both have a height of 1. Now if I try 1 plus x, the first two terms, notice it matches all the way up to the first derivative now. It looks like it's got the same slope at that point. If I include the quadratic term, it's getting more like the red function that I have here. If I go up to 1 plus x squared plus x cubed, turn that graph on, notice it's even closer. Right, compare those two, see how far away the purple was compared to the black. The black is getting even closer. If I turn both of those off and go up to the 4th degree, it's even closer. The 5th degree, I decided I got tired of typing in every single term, so I wrote a summation. Just by typing the word sum, it automatically turns that sum. In fact, I'll show you if I delete this what happens if I type that. If I do y equals the sum from n equals 0, tab, up to a capital N of x raised to the nth power. And I want to add a slider for my values of n. And let's say n can go from 0 all the way up to maybe 30 with a step size of 1. Enter. And so this, if n is equal to 1, looks like number 3 up here, just like that. If I go up to n equals 2, it looks like this 1 plus x squared. N equals 3, 4, 5. I got to 5. Now look what happens as I keep going. It's closer and closer and closer. Now the reason it's flipping back and forth over here at the left-hand side is that it's still a polynomial, which means it obeys all the properties that a polynomial has, which has in the behavior. One of the things you learn in college algebra, or should have learned in college algebra, is that as you go to negative infinity for an odd power, if your leading term is positive, then you're going to have a negative infinity. It's going to go down to negative infinity. If you have a positive leading term and your power is even, you're going to have positive in behavior, means it's going to go off to positive infinity, right? That's x to the 24th. As n gets large, negative is still positive, so it goes up and then keep going. Boop, 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 boop. Okay, that's what happens. We get closer and closer and closer to, but never exactly equal to 1 over 1 minus x. You have to have all the infinite terms, that n has to go to infinity in order for it to be exactly equal. So in order for it to be a power series representation, you have to say the sum as n goes to 0 to infinity for it to be actually equal to. Which brings up a good point. If I scroll down to the top of the next page, there is a distinct difference between saying something like, oh, and these are a typo, that should say minus right there, my bad, that's minus. To say 1 over 1 minus x is approximately equal to 1 plus x squared plus x cubed plus x to the 4th, say I stop. That's why I put a curly equal sign. It means it's only approximately equal to. On the other hand, to say equal to, I would have to say that this thing not only has these 4 terms, but keeps on going forever. It has to have the sum from n equals 0 all the way up to infinity, whereas this one stopped at like 4. Okay, in order for it to be exact, it has to go all the way to infinity. If you ever stop short of infinity, no matter how big that number is, it's only ever approximate. In this example, we want to express the function 1 over 1 plus x squared as the sum of a power series. And also, while we're at it, let's go ahead and identify the interval of convergence. So you've got to notice in this case that it's actually very similar looking to the function we've been working with, 1 over 1 minus x. Right? You've got a similar layout, only it's not quite the same. So how might we make them look the same? Well, notice that if I were to put, instead of an x here, a minus x squared, then what was 1 over 1 minus x is now the same as 1 over 1 plus x squared. Recall that 1 over 1 minus x was 1 plus x squared plus x cubed plus ... as long as the absolute value of x is less than 1. Well, now everywhere there's an x, we're going to put a negative x squared. So this becomes equal to 1 plus a minus x squared. Oh, try that again. Minus x squared, right? That's this term here. And then this one will be plus a minus x squared squared. Okay, replace this x with a minus x squared cube, and so on, so long as the absolute value of not just x, but minus x squared is less than 1. Okay, so let's simplify this a little bit. This becomes equal to, that's still just 1. Okay, minus x squared is minus x squared, plus a minus x squared squared. The squared takes care of that minus, because 2 of those makes a positive, and that becomes plus x to the 4th. And this becomes minus x to the 6th, plus ... And then I can actually get rid of most of this, because if you take the absolute value of a negative, you still get a positive, right? And to say x squared in absolute value is less than 1, just square rooting both sides, kind of, using a little bit of algebra here, we know that if the absolute value of x squared is less than 1, then the absolute value of x is less than 1. Which I could rewrite this. This is perfectly good answer right here. I could rewrite as a summation by just recognizing the format of these terms. This looks like the sum from n equals 0 to infinity of an x to the 2n, where each term is negative 1 to the n, right? It's an alternating series, positive, negative, so that's where the negative 1 to a power comes in, and since it starts with positive, then n to the n equals 0 gives me a positive, so the first term should be positive if I plug in n equals 0. So I don't need an n plus 1 is basically what I'm saying here. And then these powers are the even powers. I mean, you can also see from maybe right here, maybe this is an easier way for you to determine the summation format, is that one is the sum from n equals 0 to infinity of x to the n. That's 1 over 1 minus x, and then if we replace that with a minus x squared, you get the summation from n equals 0 to infinity of negative x squared to the n. Okay, so the minus can come out as a minus 1 to the n, and the x squared becomes squared to the nth to the 2n, which is exactly what I wrote right here as my final answer. And that's handy to know, because that's going to be the form that your homework asks you to put it in. All right, now the next one is not quite as challenging, I don't think, because we actually don't have to do anything to get this form here to look like the 1 over 1 minus x. I'm going to do that in some of these later examples. But if you've got a polynomial, the good news is it's actually already, all polynomials are already in their power series form. You might just write it like this, that f of x, let's do it in increasing order or power. So the 6 is the 0 degree term. The first degree term is a minus 5x. The second degree term is plus 3x squared, and then plus x cubed. And now what's the x to the fourth term for this function? Well, there's not one. So if there's not one, what would we put in here as, say, the coefficient? If I want to put an x to the fourth in here, I hate when it smooths for me, x to the fourth, then what's its coefficient? Well, that's wrong. That right here, as I've got it written, it is not the same thing as this function. That changes it significantly. Unless I do this. Put a 0 in there. And a 0x to the fifth. And a 0x to the sixth. It's still a power series because they all have coefficients, but we're just saying there's 0 from that point on, right? That, if you're writing this like the sum cn x to the n, your c0 is 6, your c1's a negative 5, your c2 is a 3, and your c3 is a 1. But for cn after that, where n is greater than 3, they're all zeros. So this right here is the power series representation of that polynomial. Next problem. We've got, what is the power series representation for the following function? We've got 1 over 3 plus x. Alright, so now we got to get tricky here. So how do I get this to look like a 1 over 1 minus something? Because if I could do this, then I can take whatever is this something and stick it in for x, like I did up here, right? I can plug that something into these little x's right there. So how do I do that? Okay. There's a couple of choices here. I'll let you think for a minute. Actually, I'm not going to stop the video for a whole minute, but you could pause and see if you might think of how I might get this to look like something like this. The first suggestion I have would be this 3 is what's complicating things, so let's factor it out. If I pull that 3 all the way out, pull that 3 out and factor what's left, I've got 1 plus x over 3 behind, and I can pull that out as a 1/3. So it really looks like this: 1 over 1 plus x over 3. This is the same as that function right there. Just pulled that 3 all the way out. Okay, and to go one step further, that looks like a 1/3 out front over a 1 minus a negative x over 3. Now here's my 1 over 1 minus something, which I could then plug in. Now that right here will look like a power series using my known geometric series. It looks like 1 plus a negative x over 3 plus a negative x over 3 squared plus a negative x over 3 cubed plus and so on, but not for all x, only for x's where the thing that I plugged in, a negative x over 3 in absolute value, is less than 1. Put this close parentheses right there. Alright, so let's do a little bit of simplifying. I'm going to multiply in the 1/3 to every term, and I'm also going to raise all of these powers. Okay, so 1/3 times 1 is 1/3. That becomes a minus x over 3 squared. This becomes a plus x squared, because minus times minus is positive, over 3 cubed. This becomes a minus x cubed over 3 to the 4th, plus, and so on. So as summations go, this would look like the sum from n equals something to infinity. I think I'll go with 0. You have a alternating series, so it's a -1 to the n. That's going to give me positive, negative, positive, negative, positive, negative. My x's are all to the nth power, and my 3's are all to the next higher power, 3 plus 1, n plus 1. Now, last thing we got to do is worry about this over here. So, first thing I notice is an absolute value of a negative is still a positive, so that's the absolute value of x over 3 is less than 1. But I could separate that out and make this absolute value of x over absolute value of 3, but absolute value of 3 is just, where'd my mouse go? There it is. 3, and then multiply that to the other side, which means the absolute value of x has to be less than 3. So this function here, 1 over 3 plus x, is the power series, the sum from n equals 0 to infinity of -1 to the n, x to the n over 3 to the n plus 1, for all values of x where x is between -3 and +3. That is from absolute value of x is less than 3. I think I said absolute value is between those, but what I meant was x is between -3 and +3, or we could say it like this. So there we go, boom. My radius of convergence turns out to be 3 in that case. All right, so we got another one that's still asking us to find the power series representation of this function. So what I notice in this particular case is that I can write this as like x, pull it out front, 1 over 1 plus x, because x plus 1 is 1 plus x. So if I could find a power series representation for this guy, then I can just distribute the x to every single term. And of course, I need it in terms of 1 over 1 minus something. So the only way to make 1 over 1 plus x look like 1 over 1 minus something is to make that a minus x. So this looks like x, and this becomes 1 plus a minus x plus a minus x squared plus a minus x cubed plus a minus x to the 4th, and so on, for whatever I'm plugging in, the value of that inside the absolute value is less than 1. So this is equivalent to x times all of this. So if I multiply in the x and also do all of the powers, I end up with an x times 1. That becomes a minus x squared, a plus x cubed, a minus x to the 4th, a plus x to the 5th, minus, and so on. So if I want to write that as a summation, oh, and by the way, absolute value of negative x is just absolute value of x, so that's still just for the absolute value of x less than 1. Then, let's see, we can start at, you can do this a couple of ways. So it looks like my power, if it's just going to be n, I could start at 0 and start at n plus 1 up here and then make my -1 to the n. Or I could have done the sum x to the n and start at n equals 1, still go to infinity in both cases. But I can't do -1 to the n because 1, if I plug it in first, makes the first term negative and first term is positive, so I'd have to do like n minus 1 up here, or n plus 1 works. Either one of these two is correct. All right, one last example. Actually, this one's not all that different than the earlier ones that we've done because it's just a combination of things. So you've got the 3 that you got to handle here, and you've got the x squared that you've got to handle here. I'm not even going to work the whole problem. I want you to kind of fill in the gaps on your own with your notes, but I will do this. I would rewrite this as 1/3 pulled out of 1 over 1 minus an x squared over 3 negative. Okay, that just takes a little bit of algebra to see that this is equivalent to this. And then we can plug that into my power series. Okay, and when it all falls out, what you should end up with is a sum from n equals 0 to infinity of a -1 to the n. It's going to be alternating because there's a minus sign in here. You're going to have an x to the 2n from here, and you're going to have a 3 from out here, but also a 3 from in here. So that becomes 3 to the n, and then one more 3 makes it 3 to the n plus 1. Okay, and you got to work this out too, but that turns out to be where the absolute value of x has got to be less than the square root of 3. So try following the same process as before to figure out what goes in right there to get us to this point to check your answer. So here becomes the crux. This is the meat. This is why we do what we do with power series, because there are things that we can do with functions that are easy if they're in their power series form, or if we have a power series representation for that function, that may be enormously difficult if it's in its original closed form. We are able to differentiate and integrate power series using a term-by-term differentiation or integration approach. So, I mean, it's pretty simple. You're thinking of it in terms of the rules for integration, rules for differentiation. The key rule is that if you have a constant times a function, then the derivative of that is a constant times the derivative of that function. If you have the sum of two functions, then the sum of the derivative is the derivative of the sum, or vice versa. The derivative of the sum turns out to be the sum of the derivatives. So if I wanted to take the derivative of this function f and I had a power series representation, then all I got to do is take the derivative of each term individually, and then I have a power series representation of the derivative with the same interval of convergence. That's a just fabulous result. Okay, so let's state the full theorem. If we've got a power series that has a radius of convergence r greater than 0, then the function that's given by that power series is differentiable and therefore continuous, and because it's continuous, it's also integrable. So if we can take its derivative and we can take its integral, we can actually have a technique to do it. So look at this power series, and let's just take the derivative of its terms. What's the derivative of C0? C0 is a constant, so the derivative of the constant is 0. So there's no C0. What's the derivative of C1 times x minus a? Well, think of this as you could do it almost like a chain rule. It's got a raise to the first power here. 1 times C1 times x minus a, now to the 0, but that's just a 1, so you have a C1, okay? Plus, ooh, where'd that come from? Try that again. Plus, now take the derivative of this term. Bring the 2 out front. 2 C2 times x minus a, now to the first power. Okay, the next one, even though I don't have it written down here, would have been a C3 x minus a to the third, so you get a 3 C3 x minus a squared, plus, and so on. If I write it in summation form, that's from n equals 1 to infinity, not 0, because I start with C1, so I'm going to say Cn. It's going to have an n out front. Notice 2C2, 3C3, the next one would have been 4C4, so it's NCn x minus a raised to the nth power. The integral can be found by taking the integral of this whole thing. I'm going to do one thing backwards. I normally take an integral and then add the constant of integration at the end, a plus c. I'm going to put the big constant of integration, which I'll call capital C, at the beginning, and then integrate. So I don't have to put a capital C at the end of a dot, 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 because you put something at an end of a dot, 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 and you think, well, that it ended it. But the dot, dot, dot means it has to go on forever, so it's better to put that constant of integration at the beginning. Now let's integrate each one of these terms. So the integral of f of x is the integral of this power series. The integral of a constant is a constant times x. Okay? But so that it looks like the rest of these, I'm going to do something a little tricky and say it's a constant times x minus a. And it's still true, even though it looks like I cheated, because it's c naught x, but notice if I take c naught times minus a, I get c naught times a, which is a constant. So if I took its derivative, it's 0. So I can confirm the derivative of this is just c0. So long as that's true, then I've also found the integral of it, right? I found the integral of c0 is c0 x minus a. That keeps the pattern of everything the same. Like I said, it's a little bit of cheating, but, you know, it's still true. The derivative of this is c0, so the integral of c0 is this. Okay, that's it. What's the integral of the next term? Okay, well, I've got an x minus a to the 1, so I'm going to increase that by 1 and divide by it, so I get a c1 over 2 times x minus a squared. You can confirm if I take the derivative of this, I get this guy right here, because the 2 out front cancels with that 2, c1x minus a then to the first. The next one would be c2 over 3, x minus a to the third, and so on. So if I write that in summation form, actually, I tell you what, before I even do that, I will write c for the constant of integration plus, now the summation from n equals 0 to infinity of cn over n plus 1 to the x times x minus a to the n plus 1. And there's my integral of a power series, and there's my derivative of a power series. And again, as I said before, the beauty of it is that the radius of convergence for the power series, in both cases, stays the same. If the interval of convergence was given by the radius up here of r, then the radius down here is going to be r. All right, so let's do a couple more examples. In this case, what I'm going to do, I'm not going to take the derivative of the function. I'm going to use my knowledge of the geometric series we've been working with to come up with another way of representing, or I guess rewriting, manipulating a given function, like this doodad right here. We want to make him look like, as before, 1 over 1 minus x. How can we get this to look like this? And so it takes some creativity. I told you, this chapter is the clumsy chapter, because whatever we got to do, we got to get it back in terms of something like this. So why is this like this? Well, it's close, but you can't just, find something to plug in for x from this. But, aha, there is a relationship between these two functions via calculus. Okay, notice. What is the derivative of that function? Okay, so forget this mess for a second. What's the derivative of that? It helps, you can write it as 1 minus x to the minus 1. If you want to take its derivative, you would take the minus 1 out front, right? 1 minus x to the minus 2 times the derivative of what's inside the chain rule makes that a plus, because the derivative of 1 minus x is minus 1. So this is essentially 1 over 1 minus x denominator squared, right? Because 1 minus x to the minus 2, that's 1 over 1 minus x quantity squared. What? That's the function we're looking for. So I could take the power series of 1 over 1 minus x, which is 1 plus x squared plus x cubed plus x to the fourth plus dot dot dot. And take its derivative. And guess what I will get? I should get the function 1 over 1 minus x quantity squared. So instead of taking the derivative of this, let's take the derivative of its power series, which we can do in a term-by-term way. The derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed, 3x squared. The derivative of x to the fourth is 4x cubed, and so on. Okay? So in summation form, it looks like this. Okay, you've got an x going to a higher and higher power, and you've got a number out front which is one more than the power. So let's do this. Okay, and if I start at n equals 1, that will give me a 1 times x to the 0, which is this one term. Of course, that's gone, right? And then n equals 2 gives me a 2x to the first. Voila. And so on, so that goes to infinity. And of course, the interval of convergence is the same as it was for this power series that I was working with. So it's still absolute value of x is less than 1. There is the power series representation of this function. Okay, here's its expanded form, and here's its summation form. Either one of them are useful and can be worked with. We want to just make sure that we can fluently convert between this and this. But yes, 1 plus 2x plus 3x squared plus 4x cubed, that's the expanded form of the power series for that function, which is what we were looking for. And this is what it looks like if you write it as a summation. It's beautiful. But it takes some creative, Observation, you have to recognize that this turned out to be the derivative of a function who we know its power series for. It gets harder and harder. How is this related to 1 over 1 minus x? How can I get from this to something like this? Well, I do notice that I can recall that the natural log, not the ln, I don't know where I got that, the natural log of 1 plus x is the integral of 1 over 1 plus x. And you're like, where did he pull that out of? Well, I kind of pulled it out of thin air, but it's something that I remembered. Natural logs have something to do when they're take the derivative of a 1 over something, right? Natural log of x is the integral of 1 over x. So if there's a 1 plus x, then I got a 1 plus x. And then I know I can do this, would be the integral of 1 over 1 minus a minus x dx. Okay, which means the integral of 1 minus x plus x squared minus x cubed plus x to the fourth, right? By putting a minus in here turns it into an alternating series. But then I'm going to integrate. So I have a c for constant integration plus the integral of each one of these guys. So x minus x squared over 2. I hate when I get sloppy. X squared over 2 plus x cubed over 3 minus the integral of this, which is x to the fourth over 4 plus x to the fifth over 5 minus and so on, which is like c plus the sum from n equals, let's do 1 to infinity, and it's like x to the n over n. I got a negative 1 out front, but the first one is positive, so I got to do an n minus 1 up there. All right, I'm going to clean this up. Sorry, it's a little sloppy. I'll write that one more time. C plus the sum from n equals 1 to infinity of negative 1 to the n minus 1 x to the n over n. Okay, but there's no c here, so what does this c right here mean? We got to get rid of that. This is equal to this, so let's see what c is equal to by just picking a value of x that we know. Like, for example, if I let x equal 0, then what's the natural log of 1 plus 0? That's just the natural log of 1, which we know is itself 0. So that says if I plug in x equals 0 into this, I should get the same thing as if I plug in x equals 0 into this. Okay, so plugging in 0 into this, I get c plus, and that's 0 for every one of these terms. I plug in 0 here, 0 here, 0 here, 0 here, 0 here. They're all zeros. So I get 0 equals, has to equal this same 0 here. So that means that c is 0. So that's actually gone, which means this is your answer. And since I started with this guy right here, whose radius of convergence or interval of convergence is given by that, then that's also true down here even after I take the integral. Let's do one last example. Okay, so you've got the same problem again. What is the connection between this function here and 1 over 1 minus x? And this one takes you a little bit longer. Maybe you go and you pull out your calculus book, or you pull out your reference pages, and you're trying to find anything that has this guy in it and something that looks like this. And digging enough, you'll find this thing. Recall that the integral of 1 over 1 plus x squared dx is the arctangent. And we've already found this guy in an earlier example. He's 1 minus x squared plus x to the fourth minus x to the sixth plus x to the eighth minus and so on. So if I integrate this, I will get arctangent. So I get c plus x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. This right here is the arctangent, except I need to find what c is. So let's let x equal 0. That means arctangent of 0 is 0. So it also means that c plus 0 has to be 0, because I plug in 0 to all of these, I get 0. It has to equal this 0, so set that equal here. So c has to be 0. So arctangent is x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. It's kind of a well-known one, fairly well-known. It's about 5th on my list of power series that I know off the top of my head. Okay, so how would I write that in summation notation? What I would do is I'd just kind of reverse engineer this guy. Notice that my powers are all the odd powers. So if I start with n equals 0, then it's like x to the 2n minus 1. That's an odd number. Plugging in, 2n plus 1. Plug in 0 into that, you get 1. Plug in 1 into that, you get 3. Plug in 2 into that, you get 5, and so forth. And so that's each one of these fractions, but then I've got the alternating part. So negative 1, and n equals 0 is positive, and I want that to be positive. So n equals 0. If you put 0 in the power, that's going to give me a negative 1 to the 0, which is a positive 1. So that matches here. Voila. Hope I explained that well enough. The key here, really this example is showing you, we can go from here to here, and then this is how we find our c. This is how we integrate. Alright, so I want to do one more example, and it's actually very much like one we've already done, so this is not going to be that hard. It's the second part of this that I'd like to just show you one of the results that we can get out of this to be able to do things like approximate values of integrals. When we have their power series, and especially when they turn out to be alternating power series, it makes it very easy to figure out how many terms we need in order to get a certain level of accuracy when we start approximating integrals using power series. It's a new way of approximating. You've talked about at some point in this class, we've done the Simpson's rule, we did the trapezoid rule as a way to approximate the value of an integral, but there's another way, is if you can get it in terms of its power series, then you can just go so far in the power series and then stop and use that as a way to evaluate, to approximate that integral. Okay, so let's do the integral from, this is just an indefinite integral of 1 over 1 plus x to the 7th as a power series. So it looks like this, integral dx. So treating this as a power series, we're going to let in our geometric series, we're going to let our ratio be negative x to the 7th. So 1 over 1 minus a minus x to the 7th gives me a 1, a minus x to the 7th, a plus x to the 14th, because you're going to square it. Right? A negative x to the 7th squared is a positive x to the 14th minus x to the 21 plus and so on dx, which gives me a c plus x minus x to the 8th over 8 plus x to the 15th over 15th minus x to the 21 over 22 over 22 plus and so on. Or we could write that in summation notation. Again, the negative x to the 7th in absolute value has to be less than 1, which is again the same as saying that 7th root of 1 is still 1. I might write this as x. These are all 1 more than a power of 7, so not a power, a multiple of 7. So 7n plus 1 right? If n is 1, if n is 2, if n is 3, that's 8, 15, 22. And the number on bottom is the same, so 7n plus 1. I'm starting at n equals 0, going to infinity. Starts positive, so I'll write that. There it is as a power series. Okay, now it asks us to approximate a definite integral from 0 to 0.5 of this power series. So since we have the antiderivative right here, we have it as a function of x, we can plug in 0.5 or a half into this and 0 into this and subtract the 2. When we do that, the c's are going to cancel, because if I plug in 0.5 in for x here and plug in 0 in for x here, then you subtract, they both have just a c, so those subtract out. And also, when you plug in 0, this becomes all 0. So what we actually end up with is that the integral from 0 to 0.5 of 1 over 1 plus x to the 7th will be, and I'm going to treat this 0.5 as a 1/2, is I'm going to plug in this 1/2 into this thing. Actually, what I'm going to do is I'm going to plug it into this one here. Alright, so plugging in here, and then plug in 0 and subtract, that c's gone, so then I have that x is a 1/2 minus, this is a 1 over 2 to the 8th, and then you've got a times 8 in the denominator, and a plus 1 over 2 to the 15th, and a times 15 in the denominator, minus 1 over 2 to the 22 times 22, plus, and so on. So the question now is, where do I stop? At what point do I stop adding? Because I could do 1/2 as an approximation, then I could subtract this, and then add this, and then subtract this, and keep going. The next one would be 1 over 2 to the 29th times 29, and then a minus, and so forth. Where do I stop to get this level of accuracy? Well, you recognize that it's an alternating series, and back when we covered alternating series, we had something called the alternating series estimation theorem, which said that the error for a partial sum of an alternating series is less than the absolute value of the next term. So if I did this, then the error is less than this term. If I did these two, then the error is less than this. If I did these three, then the error is less than this. Okay? So whatever the size of the next term is, you will know that that error is going to be less than that. So what I would do is I'd just figure out how big each of these terms are. So for, say, this term right here, if all I needed was a half, what is 1 over 2 to the 8th times 8? Well, that's, I plug in my calculator, it's about 5 times 10 to the minus 4. That's too big. Okay? 1 over 2 to the 2 to the 15th times 15 is about 2 times 10 to the minus 6th, which is still too big. And then 1 over 2 to the 22 times 22, that's this term, is about 1.1 times 10 to the minus 8, which is smaller, which means I only need to add these three terms up to get the approximate value of this, which I did with my calculator, and I got 0.4995137.4. This is the approximate value, accurate to within 10 to the minus 7 accuracy. And I just found that using the alternating series estimation theorem together with my power series to be able to find that integral accurate to 10 to the minus 7. All right, and that's the clumsy way. Let's come back and do the elegant way. Probably my favorite section in all of Cal 2 and all of calculus as a whole, maybe in all of undergraduate mathematics, is coming next in 11.10, the Taylor series. I love the Taylor series.